Good evening, everyone.
Good evening,
I'm
Mr. Dan.
Uluwadamlola. So just give me a minute to share my screen here. Okay. Okay. Can anyone confirm if they can hear my screen? Oh, sorry, if they can see my screen rather.
Yeah,
Yeah.
yeah, we can see
All
you.
Yes.
right. Yeah. Okay. Sorry. Yeah. Good evening, everyone. I'm Damlola. I'm a software engineer from Lagos here. Yes, so today we'll be speaking about engineering reliable payment flows in Java. Three major points: precision, idempotency, and security. So, like Samuel said a few minutes ago, definitely Java is not dead because if you've been opportuned to work in financial technology in Nigeria and even outside Nigeria, the go-to language is still Java. So Java is very mature, Java scales, and Java does the work without so much. So um, let's just get into it. So first off, I want us to just
Hello, Mr. Dami, we can't hear you. I think probably if you're having network issue, you can just switch off your camera. I think you can switch it off to reduce the network. Can you hear me? Apologies everyone for the network. We'll be joining us shortly. Thank you, Oscar. We'll be joining us shortly. Okay, okay. I think it was a system issue. You'll join shortly. It was a system issue. rejoin shortly. Apologies for that. Apologies. Okay, he has joined, so you are welcome, Mr. Dan. You are muted. You are muted. You are muted.
Yeah, I'm very sorry about that. My system glitched
Yeah,
for a
yeah, yeah.
minute there. Yeah, back. All right. Just I'm getting the. All right. So back to it. Yes. So why is payment engineering hard? So first off, I'm going to assume that I'm talking to a lot of technical people here, but I won't really be talking from the code perspective. I'll be talking more from a business perspective because engineers always like to just get in and write code. But when it comes to payments, you need to understand the business and you need to understand how money flows. So when you can understand those problems, then you can now translate it to code. We'll be looking at a little bit of code, but it's mostly going to be understanding the payment architecture, what exactly happens behind the scenes, and why we do what we do before we look into the code. So why is payment engineering hard? We have we tried callbacks. Maybe your service is down. Your providers might try to call you back a couple of times, and then um, different problems could arise because of that. We have risk conditions. One, you're trying to update something and something else is running, and then you do not cater for that when you're writing code. Yes, we have that problem in multi currency a lot. So sometimes in some rare conditions, you see your code conflicting each other and just messing you up. Yeah, so we have partial failures. So you could have oh sorry.
We can see your screen, Mr.
Okay.
Olakunle. You have to join. You have to rejoin. Is anyone else? Please, if you are having that
And
issue,
I can see
then
his screen just fine as well.
yeah, I think you
Okay.
have to rejoin. By the way.
I can see screen from here also.
Okay, good, good.
All right. So we have partial failures. Partial failures in the sense that maybe you're trying to build a transfer service and a customer is debited, but this transfer is not later successful, so you don't credit the other customer. That's a partial failure because a part of the transaction was successful, but the second part wasn't successful. So we have to guide against that. We have double debits. I don't know if you've ever sent money out or if you ever paid for something and then you see that you were debited twice and now you have to go to a bank. We have to engineer our systems to be resilient to not encounter this kind of issues. Network issues. I mean, just a few minutes ago, my network dropped off and I had to change and come back. Yeah. So in Nigeria, we have this a lot, network issues. I would say most of our problems in payments is actually due to the poor service our ISPs give us. So you have that, and you have to still walk around and engineer your systems around this problem. We have fraud attempts all over the world. There's fraud in Nigeria, particularly in Nigeria. There is more fraud. So when you are building your systems, you have to think about how it could be broken into. You think like an attacker and try to protect your system against this. We have precision errors, which is even the first thing we're going to be talking about in this meeting. We're dealing with money, and money has some values that you might like to call decimal values, but we don't treat decimal values of money the same way we treat any type of decimal values. You understand? So because if you're adding 0.01, 0.01 of on every transaction, over time to pile up. I don't know how true this is, but I know a while ago in Nigeria they said that there was this guy that was debiting customers' accounts, I think 0.01 naira, and over time it became a very large amount before they caught him. So I'm just trying to bring it to you that those tiny errors could pile up, and before you know it, business is losing a lot of money. We have time-based attacks. These are attacks where your attackers can call your system multiple times. They're timing and they're calling your system. They're trying to get some keys. They're trying to decode some keys based on the response time that your system gives. It's also a very common attack that we need to protect against. So let's just go into it. So we have the core requirements of reliable payments flow. So the first one is deterministic results. And what does this mean? If I'm integrating with a payment service, I want to know exactly what I'm going to get at every given time. That's why if you are integrating with most payment service, the first thing you would even get to see is a documentation or a specification. I can remember when I resumed my recent job currently, for like the first 1 month, I was told to just read the specifications. And at that point, I was like, I'm here to write code. I'm here to do a lot, but they were like, just read the specifications, just be familiar with all the systems and the code that they return. So it's very important to just know that if I'm calling your system, this is exactly what I'm going to get for every situation. If it's a failure, if the account could not be found, if it's an insufficient balance, I have to know that I can map everything you're going to return to me to something on my system. Yes, so that's the first one. We have no double processing. We don't want to process transactions 2 times. There might be different things that might cause that. A service might be down, there might be network issues, and then the request fails, and then the provider tries to send you another transaction, and it goes into your system as a new transaction. We don't want that happening, because the provider will say, I sent it to you only once, and you'll be saying, I saw it twice and I processed twice, and then somebody's going to fall out of pocket in most scenarios. We have accurate money precision. So the person that is calling you or the person you are calling does not really care about the inner workings of your system, how you are handling transactions internally. What they really care about is, if I give you 5,000 naira, and I hope you're not going to come back to tell me that I gave you 50,000 naira. They want to make sure you are handling money in a precise manner. Yes. So the next thing is safe retries. Also, people that are integrating with you, or even if you're just building for a front end, the front end wants to know that the people that are integrating, if I send you the same thing, like if I call you and then you fail, if I try again, I want to have this assurance that you will not go and pick down my former transaction and pick this new one and run it. It's more like double processing, but this one is on the client side. You could have a bug within your system that makes transactions process twice, but this is from the client side now. So you don't want your providers to call you for the same transaction different times and then you're processing it multiple times. It's that simple. Then secure signature verification. So this just means that when you're opening an API for people, especially for callbacks, you have to make sure that you know who is calling you. and you can verify who is calling you. So if I'm opening, okay, let's give an example. If you've integrated with Paystack system or Stripe, they have a callback implementation. When a payment is done, they call your system. But that endpoint is open on the internet. It means that anybody can call that endpoint. Yeah, anybody can call that endpoint. But how do you verify that this endpoint is actually coming from Paystack? That's where signature verification comes in. Audit logs. This is one of the most important things in payments. So most times we write code, yes, and a lot of us are just interested in writing the code. But after this, your code goes to production. This is what is going to save your system. So when your code goes to production, your code will go through a bunch of testing. But when anytime code goes to the real world, there are a lot of scenarios that you can't always cater for doing development. So at every point in time, you should always be able to go back to logs and know what happened on the system. What transactions came in? Where did it go out? More particularly, what change happened on the system? So imagine if you have some kind of variables that changed from, there's an admin dashboard that you can go and change some things on the system and cause transactions to process a different way. For example, maybe you process transactions coming from, maybe you process transactions below 50,000 to Paystack. There may be transactions above 50,000 to Flutterwave. That's how you configured the system to work. And all of a sudden, we're seeing that Paystack is getting transactions above 50,000. You would want to go back to your logs and now look at your logs that, okay, what happened at this point in time? When did the configurations change? And that's the only time you can really tell, okay, this is what happened, and then you start running a fix, or at least you know where the problem came from. Yes. So we have a double entry ledger. I'm going to be talking about this later during the session, but it's kind of an accounting standard where you make sure that when the transaction comes in, you're not just going to go and store it somewhere in the database, especially when you're building a payments system. You want to make sure that you're treating it like an accounting book. You're debiting the money from somewhere, you're crediting the money from somewhere, but I'll go more into that later. Replay protection, traceability. You don't want people calling your endpoints to know what's happening behind the scenes, and you want to be able to even trace requests. You want to be able to see all the requests that came in through your system. All right, so I'm going to be focusing on one particular architecture. So the whole flow would be streamlined and we can just go through it. So this is an architecture where a client calls a payment provider, the payment provider calls your webhook, and then your backend does some verification. Your ledger, you put the entries into your ledger, you process, and then you settle, whether you're paying out, whether you're just adding to a user's balance. But this is the flow I'm going to be focusing on. So let's go. So the first thing is precision. That's the first thing in our topic, precision. Why should you never use double or float? So many people, when they see number, I remember when I started writing code, when I see numbers, I just used to assume that when I see a number that has dots, it's just going to be float, it's going to be double. I assumed that even then I thought that full numbers too were supposed to be integers or something like that. But there are certain rules and there are certain things regarding that determines how you assign data types. So the first thing is that why are we not using numbers, double or float? So I don't know if anybody has ever tried to play around with code, and then you do something like 0.1 plus 0.2 or 0.01 plus 0.02. You would notice that you won't see, your result would not be 0.03. Your result would be 0.0 0.03000000, maybe 1 at the end. That's just one representation of this problem. So when that happens, how are you sure that over time that 0.001, 0.001 is not pile up and maybe one day enter a billionaire? It's just a matter of time. It's going to happen. And the reason is because double and float are precision types. They are made for when you don't want to lose values. Like now, if you were designing a rocket system, I would not expect you to use big decimal. I would expect you to use double. You want to be sure that you can take every digit that is coming into your system. But for money, remember we have just 2 decimal places. Everything we're doing is within decimal places. Although there are some exotic currencies, that's what they're called, that have more than 2 decimal places. But the standard of the world, the ISO standard, is that we have just 2 decimal places. So you don't want to use double or float. You want to use big decimal. I want to use it throughout your system up until storage. Now, the next thing is that we use smallest currency units. So if you work with legacy systems, if you've worked with a core banking system, you've worked with maybe SWIFT transactions, as for international transfers and so on, you'll find out that most of them do not use the smallest currencies unit. But when you integrate with systems like Stripe, you integrate with systems like Paystack, they use the smallest currency units. And there's a reason for that. When they build the systems, that's core banking and legacy systems, they try to replicate what people were already doing on paper. And people were using .00 on paper. .01, they were using 2 decimal places on paper. So they just wrote applications that were doing exactly that. But it came up with a lot of problems as regards to precision. So the rule of thumb now in modern solutions is that we build in smallest and we build dealing with only smallest units. When I mean smallest unit, I mean you store your values in kobo, you store your values in cents, you store your values in pennies. You don't want to store .00. You can decide to do that, but the new standard that most fintechs are going to is storing in currency. Sorry, storing in the smallest currency. Also, you should always define your scale. When you're storing currency, when you're working with currency, always define your scale. Meaning that if some currencies now, like Naira, if you're storing with smallest currency, that's kobo, 100 kobo make 1 Naira. You always have to define that this is how much kobo will make 1 Naira. And with all of this, you would definitely avoid rounding surprises. If you build a system like this, you would always avoid rounding surprises. Let me just pitch in something. So there are some times where you still have to integrate with these legacy systems. My advice is that always convert to the format at the last stage. It can even be an annotation, or it can be something you can just apply at the controller level or not at your DTO level, but just at the last stage when the data is going out or when the data is coming in. You don't want to get to your business logic layer and then you're writing code to now convert currency. No. You should have a standard way across your system when you're integrating with legacy systems that still send money that way. You should have a standard way of converting it to smallest units and apply it at the outermost layer, which is your presentation layer. So, moving forward, let's talk about idempotency. So, what happens when, let's use the example, a client clicks a button twice. It clicks a pay button twice. Maybe the button did not disable on time. So the client now clicks on the pay button twice. You want what the result of that is that the person is probably going to get debited twice, and we don't want that. So idempotency is saying that no matter how many times the same request comes in, I'll treat it as just one request. So it means that even if the request comes in and there's a network breach, maybe you get the request, but you don't process the request. or you get the request, but you don't respond to the sender, and another request comes in, you should be able to figure out that this is the same request I got before. And how do we cater to this? Yes. How do we cater to this? So this is a Redis-based idempotency service where when a transaction, so first off, the provider or the front end or whoever that is integrating with you should have a way to create idempotent keys. It means that if they're sending you a transaction, they should send you with an idempotent key that even when they are retrying it, it should always come with that same key. So even on a front-end system, when the user clicks a button, it's possible that they can generate a key and save in storage. So even if the person is re-clicking, they know they're still sending the same transaction because they might have gotten an error, but the transaction go to our side. That's your system, and we have processed it. But that person, we might have returned an error because maybe a 500 error or maybe a network error. Maybe a bad gateway error or something. So the person keeps clicking. Their system should be able to send you a key that lets you know that, okay, this person is trying to process the same thing. They can also protect it from the end. But in the case they're even trying to retry by themselves, they should be able to send you a unique key. So this is a Redis-based service. You can use your database. You don't have to implement it this way. You can also implement it using a database. But this is very basic. And you can set the problem with implementing into the database is that when you write the key into the database, you have to have something to clean up the table, maybe at the end of the day or something. But with Redis, you can just set the time to leave when you are writing into Redis. So you just have a claim method that goes to write into Redis. You have a store results method that stores the results after the transaction is successful or the transaction has failed or whatever happened with the transaction. Then you have another method to get results. So that would always tell you if it is unique or not. So let's look at this code now. So let's look at the flow. Some minutes ago, I talked about signature. So we're going to be looking at the signature here. Then we'll look at the idempotent logic as well. So a PSP secret is what you give Paystack or Paystack gives you, or you give your person integrating with you. Is just a secret. And a transaction comes in. When a transaction comes in, you want to verify that this signature is valid. The person that is sending it to you is going to send it in this, sorry. He's going to send it in a header. Most times it comes in a header, not with the payload. It never even comes with the payload. It always comes in the header. And I will get to that, why it always comes in the header for a minute. So the way this signature is derived behind the scenes is that the secret that you shared with your the person you're integrating with is expected that nobody knows that secret. In the case somebody knows that secret, there is a problem. So once someone sends you a request, they're expected to hash the payload that they're sending to you with that secret. Most times using SHA-256 hashing algorithm. Yes. So most times they hash the payload with the secrets. So the first thing you'll be doing is to verify at this line of code here. We verify that, okay, this payload that was sent, is it still valid? Because remember, the attacker is also trying to enter your system. They might be sending payloads as well, but they don't know your secrets. So they cannot correctly hash your payload with the secrets. So obviously, the expectation is that if the hashed payload does not match the secrets that the person sending the request sent, then this is not a valid transaction, and I would return 401 unauthorized. So let's get into what we actually do behind the scenes. So I told you that Most times we use SHA-256 because it's compact and it's still secure. So we get the secret key, we hash the payload, and then we compare. Now, normally we could just have done, because it's still going to come out as a string, so we could just have done dot equals to, also dot equals, and then we'll just get, oh, is the left side equals to the right side? If it's equals, then pass it. But we didn't do that. Instead, we created a utility function. We created a utility function. And why did we create this utility function? It's for replay attacks. So let me explain how it works. So when you use the normal Java equals function or method, it's just going to check, is the left string equals to the right string? Immediately it sees that a character is not correct, it will return an error. It will return false, rather. It will return false. So it means that if it was the first character that was not correct, it will return early. If it was the second character that was not correct, it will return later. If it was the third character that was not correct, it will return even later than the first two. So with this, attackers can start replaying your system. They'll start replaying your system. They'll start calling endpoints, the same endpoint over and over till they can guess it. And if you don't even have like a rate limiter or something like that, they can even get this in less than 5 minutes. So when you're writing an algorithm to measure signature, to verify signature, you have to always make it at a constant time. You have to make sure it's coming out at a constant time. So if it is the first 15 characters, or let me say 31 characters that are correct, and the last one is not correct, it should return at the same time that if it was the first character that was incorrect. So how do we do that? We can run a loop and basically just run for one of the inputs. We run a loop against the length of one of the inputs that are going to be the same length because it was encrypted using SHA-256. So you run a loop and then you XOR the two characters. So when I mean XOR, if you remember Boolean logic, you compare if A is equals to B. If A is equals to B, then to give you 0. So you can just return true. So that's what you basically do. So that's how you're able to confidently verify a signature, and you know that nobody is going to be breaking into your system. Not anybody can call your system. Yes. So let's go back to the controller, the webhook controller. Yeah, then the next thing, this kind of, okay, out of view. The next thing is to call back the, you undo the PSP and then you do your business logic. It's abstracted here. So you just call, I'm making sure I'm doing an idempotent check within your undo method. All right. So let's look at encryption and let's look at keys. All right, I definitely will share the slides after this meeting. I'm sorry, Samuel, can I quickly ask, how many minutes do we need for question and answers? I know we started around 8:30.
So, we need 30 to 15 minutes, 15 to 30 minutes. So,
all right. Okay, no problem. So, first of all, there are different levels of encryption and different standards of encryption depending on the kind of payment flow you are building. So if you are dealing with cards, there's a standard PCI DSS that just explains how you should handle card data. Yes. So if you're integrating with an interswitch now, they can decide that the way you're going to integrate with them is going to be different. They want to use another type of encryption. If you're integrating with MoneyPoint, they can decide that they want to use another type of encryption or something else. So it differs. But what I'm just going to do is that I'm just going to try to talk over the different levels and the different types we have as best as I can. You get, so it gives you an overview, and when you start seeing these things in high level discussions, you know exactly what's being talked about. So first of all is encryption in transit, and that's very important. That's just TLS. So use HTTPS for all endpoints, no HTTP. This ensures that your data in transit cannot be stolen. Even if an attacker steals that data, he cannot do anything with it. Now, our next level of encryption is our disk level encryption. So it means, where are you saving to? Where you're saving to, what are you encrypting there? There's some things that should be encrypted, like a password, for example. I know we hash a password, so it's still encryption to a level. So we hash a password and put it in database. I'm sure most of you that have built any authentication system, we never store passwords in clear form in the database. So that's data at rest. We'll talk about field level and column encryption. So there's certain columns, like if somebody is sending you a card payment now, there's certain fields that you must encrypt, or you should not even store at all. Like, first of all, if you're doing a card payment, you should never store CVV. Even if it's going to be encrypted with the best algorithm that you just came up with yesterday that nobody thought of, to never store CVV. That's the standard. There are other things that you have to obscure. You can store PAN for identification processes, but you cannot store the full PAN. That's the card, that card you see on the number you see on your card. So there are things like that, and there are standards around this encryption. Now, when you're encrypting, the major thing you would do around the encryption is keys. Keys. You have to, and I think, first off, if you want to go into encryption, you should try to understand the basic encryption methods. Like, you can talk about when using AES to encrypt, using PGP to encrypt, using a HSM to encrypt, whatever way you're encrypting. Most of these methods use a key, some type of key. So you start seeing common patterns, but you should know how each one works. It's very important, because when you start seeing issues surrounding encryption, you would know where to look at. So key management, there are a lot of key management systems. We have Azure Key Vault, we have AWS KMS, which is Amazon's version. We have GCP KMS, which is Google Cloud's version, and HashiCorp Vault. Envelope encryption. So envelope encryption is encrypting the data within a request. So most times when you see if you've worked with SOAP request or even XML request before, you see that there's an envelope, then the actual data is within that request. So you might not want to envelope the whole request, but you want to envelope what is within that request. So you want to encrypt what is within that request. So we have hardware-backed keys, HSM. I would want you to really look into the world of HSM, KSM, and master keys and everything. It is a very exciting world that even I myself, I'm still discovering about. So this is, I think of an HSM as a secure locker, as a secure safe that even you, the owner, you can never know what is inside. So HSMs are very, very, very secure. They're actually physical devices. So most banks, most big financial organizations, they have a HSM. And the point of that HSM is just to generate keys and decrypt and encrypt data. That's the point of the HSM. They buy the HSM for a lot of money to just keep, and all the applications, when they need keys, they just go there, they get keys, and the HSM will give them some keys that it can use to verify that it was the one that gave them that key. But it will never give them the keys actually using to encrypt data. If you try to open a HSM, you try to play with an HSM, it automatically changes the keys. So there's a software version of it called SSM, but definitely nothing is as secure as the HSM, which is the physical device. So we have key rotation. So you should have a strategy for rotating your keys. Don't use the same keys don't use the same keys for the next 10 years, for the next 1 year. You should have a strategy depending on the use case. There's some keys that are rotated on a daily basis. There's some keys that are rotated on an hourly basis. There's some keys that are also rotated on a monthly basis even. But the more data people can get in a period of time, depending they can get from your system, the easier it is for them to break your keys. So you want to have a strategy for rotating keys. Secret management, do not store secrets in your code. And do not store secrets in source control. What source control? Don't allow your secrets to go to GitHub. I'm sure most of you, when you push secrets to GitHub or when you push secrets to GitLab, it will come and shout at you that you have pushed something. No, it is very important, because that secret that you think that you pushed by mistake 2 years ago and you're still using it till today. There are scanners on the internet that scan repos very, very frequently. So that secret might be somewhere waiting for an exploit. Like I saw something recently that if you go to GitHub and you search for a particular keyword, you see a lot of OpenAI keys that have been pushed. And that is because vibe coders are just doing their own and they're just pushing to everything to GitHub, you get. So we really need to be careful about this. When you are, even for login, yes, when you are logging, you should tokenize some kind of data. For example, PAN. So if you are logging a PAN, you should never log a full PAN. PAN is, like I said before, is an identification number on your card. You can put 5, 1, 2 or something, like the first 3 digits, and then put star, 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 maybe put the last 2 digits or something. You get, always tokenize, never store the full thing and never log the full thing. Audit and access control. So we need RBAC for key access and logging key operations. So what's RBAC? RBAC is role-based access control. So you want there to be certain privileges that there might be different users of your system, definitely, but you want some people to be able to see some things and you want them not to be able to action on some things. You want some people to be able to action on particular things, like maybe something very sensitive, like changing keys, rotating keys. It should only be specific people that should have access to that thing. So you want to build a system in a way that although you have a lot of users, they are not always mates. So you make it role-based. That's the standard. So this is just a util or for AES GCM. There's still different AES variants you can use for encryption. So it just depends on what you choose. I'll be sharing my slides at the end of the meeting. So definitely you can pick this up. You can work with it, or you can find something else. Yeah. So key management, best practices. I think I talked about this. We encrypt data on key rotation, use HSM, grant minimal IAM permissions for key usage and logging. And that's what I just explained, the RBAC. So if you've worked with AWS, I'm sure you'll be very familiar with IAM, or basically most cloud platforms, you'll be very familiar with IAM. So you can also even implement them on your own system and of course on the cloud provider as well. All right, replay attacks. So first of all, it could be a legit call. So one problem, and one thing I always want you to know, all these systems that we integrate with, Paystack, Stripe, PayPal, they are not perfect systems. Sometimes Paystack might go down and they might want to send callbacks for all the requests that came in during the time that they were down, and they will now send the same request 6 times. So when we're talking about replay attacks, they're actually legitimate ones. Yes, but even if they're legitimate, you should, like I said before, you have to build your system in an idempotent way to make sure it's not going to go and do the same thing twice. So you don't want to trigger duplicate payments. You don't want to trigger duplicate payouts. You also have to add timestamp validation. That at what time, for example, if you have integrated with NIP before, you find out that sometimes you call them for transactions, and after a day, it's telling you not found. But that transaction happened 24 hours ago. So you can also implement things like that in your system. You want to implement things like that in your system. You want to make sure that if people are paying for something today, how come somebody is not sending you a request from last week? You get, so they're trying to send you the same thing that you validated before. So you have to protect against that. And definitely you should always use unique IDs for your transaction identifiers or your entries or whatever. Then if you are using webhook IDs, also store it on your transaction table. Yeah. So let me see how many. Okay, let's go. So double entry accounting. So I don't know if this is a lot of information to take in because it's like I'm talking less code. I don't know, but all right. Double entry accounting. So I'm just going to try to brush over it, but it's kind of the standard when you're working with mature financial systems. So it basically means that if money comes into your system, don't just go and pay out or don't just go and log it in a transaction table. I remember the first e-commerce website I ever built. When the transactions will come in, I'll just take it in, I'll just go and store it in my table, and I'll just minus a particular position. You don't want to do that. So in standard and mature systems, we use double entry accounting. If you ever heard about GLs, that general ledgers and the likes, this is what we're talking about there. So it basically means that when money comes in, you must be debiting somewhere and you must be crediting somewhere. When money is going out, you must be crediting somewhere and you must be debiting somewhere. Because the money is not just manufactured out of thin air. It has to be coming from somewhere within your system. It's very important. So the point of this is that at periodic checks, you can zeroize these ledgers. When I mean zeroize, you can now confirm that this ledger will, at this point in time and this point in time, let's minus them from each other. Let's compute them. Is it going to give me 0? If it does not give me 0, it means that it's either I've overpaid or I've been overcharged. So it's a very basic concept. It's a very basic concept, but it will save you a lot of problems. You see some systems, money will get missing, and then they'll have to start looking at logs for 6 months. Where if you are double entries, you can always just check periodically what happened during this period. What was our net position during this period? 0, 0, 0, 0. Okay, during this period, it now became minus 6,000 or 600,000. What happened during this period? You pick up that period and start looking at every transaction, and you will find which credit does not have a corresponding debit and which debit does not have a corresponding credit, and you're fine. That's what most of the core banking systems use today. When you talk about Finacle, T24, a lot of them, that's what they use. And although they are not using just 2 accounts in their own case, they're using a lot of accounts. But I'm trying to say, even in your e-commerce site, your logistics provider system, you can always implement this because it's actually the standard. So moving forward, I think we've gone through this payment flow already, so I'll just skip this, but let's go again. So a client initiates payments, the PSP processes at its end, then he calls you verify that he's the one calling you, you ensure that he has not called you with this same transaction before, you write into the ledger. Also, the rule of thumb is that always write into your ledger before you update the business states. So you write into your ledger before you go and provide value. That's just the meaning. So then you undo retries safely. That's very standard. It's very straightforward, but this is the standard. There was a part I was trying to work on just before this meeting, and it is atomic updates. And is atomic updates. So first of all, when you are updating, I couldn't add it, but let me just quickly talk about it. Anytime you are changing balances, anytime you are writing into a ledger, whatever you are doing, and you are doing a transaction flow, make sure it is always transactional. Make sure it is atomic. So when one thing fails in that process, you roll back everything and you end that transaction. Don't say, okay, because the credit did not debit, I will still go on and still go and do it later. It's always better to roll back roll back your updates that you have made written to the DB already. And then you can now decide to retry internally or wait for the PSP to call you again. Yes, and there are two ways you can do that. Let's talk a little bit of code, although I don't have the code sample here. You can either just write it in one orchestrator, meaning that you can just annotate one service with, one method with a transactional, then call each method that is doing the updates one by one, that is also transactional. That works. But when you're building distributed systems, it becomes a little bit harder. So how distributed systems will work is that maybe it's one service that is crediting, maybe it's another service that is debiting. How are you going to know when to roll back? When is another system entirely that credited and another system that debited? How do you do that? You can use a pub and sub kind of architecture where anytime there's a credit, it publishes an event and then the subscriber consumes that event and it tries to update. Now, if there's a failure, the subscriber would also emit an event that, CO, I failed. Then whoever is listening would now catch it and go and roll back. The subscriber would always also roll back in that case. So that's how you can build. That's called the Saga orchestration method of this flow you get. So that's how you can do that for distributed systems. So don't think that it's limited to only when you're writing a modular project. No. You can have over 70 services and still build that and still make your updates atomic. Very important. Okay, so handling PSP retries, we've talked about this as well, so I'll just be rushing through. Okay, so concurrency and race conditions, multiple callbacks. I told you Paystack can call you 100 times at the same time because it might not even be for the same transaction. So you want to make sure that as all these transactions are happening, first of all, you don't enter deadlocks. Okay, let's talk about that later. So as all these transactions are entering, you want to make sure that you're handling them, that are not affecting themselves, there are no risk conditions. You want to make sure you're doing all of that. Client refreshing payments page. This one is a common bug that I've zeroed my mind that almost all Nigerian government websites have this problem. If you have to pay on a Nigerian website, you will suffer this problem because most times if you have already made a successful payment, then you now refresh and all of a sudden it's gone. That was why the likes of Stripe and PayPal actually brought in callbacks. So before, what used to happen is that when a payment happens on a website, it will now redirect back to your website. Your website will now call your backend. Your backend will now call the service provider that, did this payment actually get to you? If they now confirm that, yes, it's got to me and it's for the amount that it's claiming to be, or you might not even confirm that, you might just get it from the payment directly, but you might want to confirm it for some use cases. So you will confirm that, then you now return successful to the front end. But what now happens when you are redirected to the payments screen, you pay on PayPal, you pay on Stripe, you pay on Paystack, and then the person now leaves the phone, or the person now refreshes and the state is lost. You never get called, you never come back to the website, so your backend is never called. So that was why this payment provider has now came up with callbacks that, okay, even if the person should leave the site, I will still call you. So most times, I like implementing the both of them. I will implement both the website and I will implement the callback. Because most times, most payment providers treat that callback service as like secondary. So it might be down for a while and you're trying to do business sharply. So if the person is still mitigates the amount of transactions that will just be coming back after 1 hour when Paystack has finally brought up that service, you get, although Paystack is very generous in their uptime. So let's give them that. So user initiating payments twice, we've talked about that. We have to make sure it's idempotent, use DB level locking. So sometimes maybe somebody is trying to buy a ticket or somebody is trying to, there are different services that might be debiting the same customer. You might want to lock a row and say that, okay, as far as I'm currently updating this row, as far as all my services are updating this row, no other service or no other thread should also be able to update this row. You might want to do that, but when you're locking, always be careful of deadlocks. Deadlock is when you lock a row and then another thing needs that row, and you also need that other thing, then your system just freezes. You have to be careful about that. You can lock optimistically. So if that means that if you know that I'm going to be debiting wallet and I'm currently updating my entries and I'm going to still be debiting the account, I might lock the account while I'm updating my entries. You get, I might lock the account row while I'm updating my entries. Then after updating my entries, I would now update the account as well. Then I'll release it for anybody to read or write into it. Then use unique constraints. That's very important as well. I don't think I need to say too much about that. So let's just have a security. I think we have just 10 minutes left. Wow. Let's have a security checklist, the signature verification, constant time comparison, HTTPS only, as I said, replay protection, strong idempotency, immutable ledgers. Nothing must ever happen to your ledgers unless the trust in your system leaves. Mandatory audit logs, strict DB permissions, validate all PSP data, and reject unknown IPs and user agents. I think this is something that should even be done at the if you are establishing VPN connection with your providers. This is something that should be done there. But if not, it gets you should reject unknown IPs. So yes, let's go to questions and answers, and these are the results just for display. All right, I think
Okay, thank
Samuel, is there
you.
a system? Yeah.
Thank you very much, Mr. Dami. That was a very powerful one. And for those of us that have been asking for PowerPoints, for the recording, we will we do this. We drop this normally. So I was wondering why you guys were asking. So we do this. We drop the recording. We get your the YouTube, and you also get the article, the well structured article on Medium. So first question. I think I saw somebody hands raised. So um, yeah, Samuel Adesonya, please ask your question. You have less than 15 minutes, so just
Okay. Good evening, everyone.
yeah. Good evening, Sam.
Yeah, thank you so much, Damilola, for the for the presentation. Yeah, it's really meant so much, and yeah, just like other says, like yeah, we learn every day, right? Even the fact that most of the things most of us has gone through this. But then yeah, I was even about to ask. I did not know you would later cover the part of the locking at the DB level, right? Which is optimistic locking rather, right? So yeah, thank you for covering that, and thank you for shedding more light to it. So my question is, um okay, I think you kind of, it's not really a question anymore. I think you've actually cleared, because I was at times I get confused, right? I used to feel like, okay, do I need to lock IDB level again after I have my I have my idempotency if implemented already on the normal on the code level, on the normal code level, now rather than doing it again on the GPA level, right? And also, at that point, does the pessimistic DB locking matters? Like, that's my question.
You are muted. You are muted. You are muted.
Yes, actually, for some kind of systems, not all systems, but when you see like high throughput systems, like systems that are receiving like 1,000 requests in like 5 minutes, or like a lot of requests like that, and there might be different use cases. Like there might be different use cases, like in a bank now, somebody is trying to debit somebody for a transfer. Another person might be trying to debit that same customer for a loan that he borrowed. You understand? Another person is trying to make a credit on that. You do not want to use states. So in some kind of systems, you still need to lock. But in most modern scenarios, making it atomic is enough, but it still depends on the use case, basically.
Okay. Thank you very much. We have limited time. So, Mr. Bright, your hands up. You can. That's your question.
Hi, good evening, everyone. Thank you very much, for this powerful session. Yeah, so my question is around the idempotency parts, right? So, the front end will always need to, send the the key, right, for the idempotency workflow. So I'm just asking, like, is there a way to make this idempotency workflow robust? As you mentioned, I thought of, okay, what if we combine the idempotency key, then along with, maybe hashing, maybe the amount sent, the sender ID and stuff, then combining both to like have like a more robust flow. Like, is that even allowed? Is something like that even allowed? Like, does it even make sense to have something like that? Or is just that key that the front end is sending, that is what is enough to maintain the idempotency? That is the first part of the question. Then the next part, you talked about rotating, like, clearing off the keys. So why do we need to clear off the idempotency keys? I think, for example, if they are using maybe timestamp or something, or will I say EUIDs, right? It doesn't really clash so often like that. So, do you get me? Do you get my question? Yeah, that's just it. Yeah. I can't hear you.
Dami, you're mute. You're mute.
All right, so let me start with the first part of your question, which is the keys. So you talked about two different things. Okay, so you said why can't we hash other things with the key? Now, we are already doing that in the signature. So when I said we hash the request payload with the secret key, that one is for security. I want to first cover that because I think I didn't do justice to that actually. So sometimes it might not be the full request payload, it might not be the whole JSON body. It might just be that we'll pick out the sender ID, we'll pick out the amount, and maybe we'll now add something else, and then we'll hash that. So after we hash that, we can always use that to verify. So it's only me and you, Bright, that knows that, okay, this is what I decided to hash. We decided when doing our setup, you told me that hash the name, the ID, and the amount. So on my own, on your own system, when you are verifying now, you would also hash the name, the ID, and amount from the payload with the secret key that we also both agreed on, or I issued to you, or you issued to me. So that's why we're able to verify the signature. We already do that for the signature. But the idempotency key is usually another header. I think I didn't show that, but usually another header. And the point of the idempotency key is not for your business level logic. It's mostly to even reject a request. It's at the presentation layer most times. So what's happening? A request comes in, and that request came as a matter of the front end clicking a button twice. That's what it is. You just want to confirm that that request came as a result of you clicking a button twice. You are not worried about, oh, did this user sorry, let me collect my thoughts there. Has this transaction been processed before? Has it been done? You're not really worried about that at that point. You just want to know, was this request sent by mistake twice? So let me talk about the front end implementation real quick. What the front end does most times, most of them, they don't even use UUID. Some people use UUID. They just use timestamp, and they will store it in a state on the front end. So if they are trying to, maybe the front end has some kind of retry mechanism, it will keep sending with that same timestamp and maybe amount or something added together. And to send it in clear form, it doesn't need to be hashed. So when you collect that request, when you collect it the first time, you can put it in your cache. You can put it in your cache. The second thing you talked about was, why are we clearing it? So remember that you're just trying to confirm that the front end did not send this request twice by mistake, or your service provider is not just trying to retry a request. So it's at that moment in time. You have other validations like a unique transaction ID, a unique reference or something that you can use to validate at the business level later. But that's what you're trying to verify. So you just reject it immediately. So it's something that you just need to store temporarily. So you can decide to put it in your database, and you can decide to leave it forever, but it's just be taking up space in your database. because that retry might come in 5 times for one transaction and to just be bloating in your database. So you definitely have to have a cleanup mechanism on that table in your database. But a cleaner approach is that you take it from the customer and you put it in your cache for the next 6 hours. You put it in your cache for the next 6 hours. Anytime you want to make a new transaction comes in, you will check, is this key in the cache? If it's in the cache, you reject it immediately. If it's not in the cache, you continue with your logic and you will still do some other idempotent check. Now, if we say we want to be doing it on unique amounts or unique all this, the thing is that somebody can intentionally send 5,000 the same time in 1 minute. You understand? So if somebody is intentionally sending 5,000 the same time in 1 minute, and you are trying to validate that and making that unique, then that means your transactions will be failing. Access Bank app has that problem, and it's a very annoying problem. But actually, that means that what they could have done is that on the amounts page, they could have created a unique key there that they'll just use to send the transaction. So if the transaction comes again, you know that, okay, it is unique. You get, but I think they use the request or something. I don't know. So we're trying to avoid again, and that's why we're putting it in the cache. So the cache automatically expires on its own. I don't know if that answers your question.
Yeah.
Thank you very much, Mr. Bright. For I don't know if you have any other question, you can pen it
Yeah.
down. We have limited time to get, you don't have to, you don't want to shift us to another meeting. So, thank you all very much the for our attendance and also for staying up to this time. We have few minutes. I don't want this meeting to end abruptly. Mr. Bright. We have few minutes. We cannot take any more questions, please.
Mr. you can just drop your message in the chat.
Yeah, you can drop your message, yeah, in the community, or you can drop it with me. I don't know. Just drop it in the community and it will be answered. Thank you very much. Thank you very much. So we want to appreciate you all for joining. We, as usual, you get it on the YouTube, and you also get the Medium article that compiles everything that's just discussed for your learning and your relearning. Yeah, we keep going, and this is how we continually go. Thank you all very much. There's also Gloria has an announcement for us. Gloria, please.
Okay. Thank you very much, Damilola, for a wonderful section. Really appreciate, and we hope to still have you on board some other time, hopefully by next year. So I know someone already mentioned this earlier, that this is more like the second to the last section, but I just want to add to it that we'll be having a section on the 23rd, but that's not going to be lightning talks. It's just going to be more like a review where you come to tell us what we are not doing right, how we are not serving you right, and how we can improve. So by next year, when we resume, we can restructure our pattern to serve you more better. So for the person that mentioned that the link is not clickable, you can search for NAIJA-JUG on LinkedIn and probably drop a message there so we can communicate with you. Thank you very much for making this section a wonderful one. Sam, you can take over.
Okay. Thank you all very much. Uh, This is a wonderful session, and like I told you, the last session for this year, the last learning session will be a banger. You'll be amazed by the level of knowledge that we dished out. This is just at the tip of the iceberg. Yet, so we have more and more of this to come. So we have 2026 is upon us. We have great things ahead, and just be on the lookout, and there are more things. And note, for those of us that want to register in the boot camp, or that have someone you feel like they should join our boot camp, um, today is the last day. In fact, tonight is the last night. Register form, and for those that have already registered, be on the lookout. From next week, you will start getting an email. So thank you everyone for being a part of this. We really appreciate you. You get the recording and you get the Medium article for us. Thank you very much. Have a wonderful night. God bless.